Ensoftec has developed a series of videos for the selection and design of stormwater facilities for land disturbance projects. In this video, I shall show you the design of wet ponds using SWMSOFTVA. Virginia Department of Conservation and Recreation, or DCR specification number 14 gives a complete description of these facilities, their performance and criteria for design, their feasibility and design applications, regional and special case design adaptations, their construction and maintenance, and community and environmental concerns for wet ponds. The pictures and tables shown here are from these specifications. Figure 14.1 gives the schematics of a typical wet pond. This includes forebay, aquatic benches and permanent pool, as part of the pond. Wet ponds are acceptable for use in the coastal plain, where the water table is within 4 feet of the land surface. Wet ponds, like extended detention ponds and constructed wetlands, are the final elements in the roof-to-stream runoff reduction sequence. They should, therefore, be considered only if there is remaining treatment volume or channel and/or flood protection volume to manage after all other upstream runoff reduction practices have been considered and properly credited. Table 14.1 gives a summary of stormwater functions provided by wet ponds. You will notice that there is no runoff reduction credit for wet ponds. Table 14.2 gives the wet pond criteria. The designer can select the baseline design, Level 1, or an enhanced design, Level 2, to maximize the pollutant load removal. Extended detention may be provided to meet a maximum of 50% of the treatment volume. The average detention time for Level 2 design is 24 hours. The total volume of all 4 bays should be at least 15% of the total treatment volume. The total water quality volume storage may be provided by a combination of the permanent pool, a shallow marsh, and/or extended detention storage. The maximum extended detention volume associated with the treatment volume may not extend more than 12 inches above the wetland cell permanent pool at its maximum water surface elevation. The maximum extended detention and channel protection detention levels can be up to 5 feet above the wet pond permanent pool. The total area draining to the wet ponds is generally between 10 and 25 acres in order to maintain constant water elevations, though less areas are acceptable based on site considerations. Ponds should always be designed with a length-to-width ratio of at least 1.5 to 1. While developing the footprint of the wet ponds, the civil and landscape designers shall ensure compliance of all internal design features as specified in the DCR manuals. SWMSOFTVA deals with the hydraulic design aspects of these BMPs. I now open the project, which we had set up in video 3. BMP 4 of Outfall 4 is in wet pond. I shall use this example to demonstrate the design steps. I go to File, Design BMP Facility. This opens the wet pond design screen. You will note that the contributing drainage area, or the site area, and the treatment volume are already populated in the screen. Occasionally, wet ponds are used as temporary sediment basins during the construction phase of the project. While the pond grading is done at this stage, the outflow structures like the risers, spillways and orifices are made as temporary structures for sediment control during construction. You will notice that there is a radio button at the top. Is the facility used as a sediment basin? If I click on No, the program will not calculate the required cleanout, wet and dry storage volumes, based on DCR's Erosion and Sediment Control Manual. These are: required wet storage volume 67 cubic yards per acre of site area. Required dry storage volume 67 cubic yards per acre of site area. Required cleanout volume 50% of the required wet storage volume. If I click Yes to the top radio button, you will notice that these values are calculated and shown. The storage summary table at the bottom gives the required volumes, their corresponding pond elevations, the provided elevations and the corresponding pond volumes. I have not yet entered the pond elevations and corresponding storages. This is my next step. I click on Compute Volume. This opens the Basin Volume Computations worksheet. This sheet has 8 columns and 12 rows. I need to fill the first 2 columns only. These are elevation in feet starting from the lowest bed elevation and surface area at that elevation in square feet. I start filling this data from the first row. I make sure that the elevations keep increasing as I move down each row. Also, as this is a pond, the areas should also increase as the elevation increases. An error message is displayed if the data is incorrect. While there are 12 rows to accommodate up to 11 feet of storage depth, assuming that the incremental elevation is 1 foot, it is not necessary to fill in all the rows. It is prudent to fill in areas and elevations up to the top of embankment. Also, make sure that the areas include all 4 bay and permanent pool areas. Having entered all the pond elevations and areas, I click the Compute button at the bottom. This will compute and populate all the remaining fields. Column 3 gives the average area in square feet between successive elevations. Column 4 gives the volume in cubic feet between successive elevations. Columns 5 and 6 give the cumulative volumes from the lowest bed elevation to final elevation, in cubic feet and in acre-feet respectively. Columns 7 and 8 give the cumulative volumes above the permanent pool elevation, in cubic feet and in acre-feet respectively. I could always click on Clear button at the bottom, which will clear all the 8 columns. This will enable me to re-enter the first 2 columns and recompute pond volumes. Exit will close this screen and puts me back to the previous screen. You will notice that the elevation required for the treatment volume is calculated and entered here. I can provide my own elevation, which would be the top of spillway elevation. I now click on Compute Storage button at the bottom. This will compute the storage volume for the proposed elevation. If I had clicked on the radio button Yes at the top, the program would have given the required wet, dry and clean out elevations. If I give the proposed elevations for these volumes and click on the Compute Storage button at the bottom, the program will compute the volumes for each of these elevations. Please note that these are required only during the construction stage, and are not part of the final design. You will notice that the program calculates the surface area of the wet pool provided, as well as areas of shallow marsh with depths less than 1.5 feet below wet pool elevation, the transitional zone with depths between 1.5 and 2 feet below wet pool elevation, and the deep pool with depths greater than 2 feet below wet pool elevation. The surface area of the wet pool should be at least 2% of the contributing drainage area. The shallow marsh area should be approximately 15% of the wet pool area, while the deep pool should constitute approximately 70% of the wet pool area. The pool depth relationships are entered as guidance only. I go to the top menu bar and click on File, Save. This will save all the data including pond elevations and areas. To print the results, I go to the top menu bar and click on File, Print. The print report, which is an Excel format, gives the results including a stage storage curve. The next step is to perform the outlet analysis. I go to the top menu bar and click on File, Outlet Analysis. This opens the outlet analysis screen. You will notice that there are 2 sections here. To the left, you will notice Orifice Details, Spillway Details and Emergency Spillway Details. To the right, you will notice that the water quality volume required is already populated. I select 24 hours from the pull-down list for extended detention storage time. I enter the maximum hydraulic head. There are 2 procedures to determine the orifice size, to hold the extended detention storage volume. The program uses the DCR method to average hydraulic head, which is the VDOT preferred method, is given in the Virginia Stormwater Management Handbook, and gives the size of orifice in inches. This size is used in the orifice sizing to the left of this form. There are 3 types of orifices for the user to choose from. 2 circular shapes and 1 rectangular shape are given. The center line elevation of an orifice should be such that the invert of the orifice should be desired minimum permanent pool elevation. A checkbox is provided against each, for the user to select. Likewise, there are 3 types of spillways for the user to choose from. A side open riser, a circular riser and the rectangular VDOT standard SWM1 riser are available. There are 2 types of emergency spillways for the user to choose from, A broad-crested weir and weir wall types are available. A checkbox is provided against each of the above for the user to select. I enter the data applicable for the proposed riser structure. I go to the top menu bar and click on File, Save. This will save all the above data. Next, I go to the top menu bar and click on File, Print. The print report, which is in Excel format, gives the results including a staged discharge curve for the outflow from the wet pond. In order to determine the adequacy of the wet pond, to hold the water quality volume and to safely convey the 2-year, 10-year and 100-year design storms, it is necessary to route the inflow hydrographs across the pond, with due consideration to pond storage and the outflow rates. This is done using the storage indication method routing procedure, as given in section 11.5.6.1 of the VDOT Drainage Manual. For the inflow hydrograph, the program uses the NRCS dimensionless unit hydrograph. In an event-based model such as the NRCS method, the rainfall hydrograph for the design rainfall event is based on the CN method, and the application of the NRCS 24-hour rainfall distribution is well documented. Now that I have the inflow hydrograph, the staged discharge curve and the staged storage curve, I go to the top menu bar and click on File, Generate Hydrographs. This will produce an Excel spreadsheet, which provides recursive computations for the storage indication routing. Inflow and outflow hydrographs are generated for the 2-year, 10-year and 100-year design storm events. For retrofit EMPs with pre-development site areas and inflows, the hydrographs for existing conditions are also generated. If I go to File, Summary Table, a new screen opens giving the drainage areas, pre- and post, rainfall depths, peak discharges and the corresponding water surface elevations inside the pond for the 2-year, 10-year and 100-year design storm events. The next step in the design of wet ponds is to perform outlet analysis. I go to File, Perform Outlet Analysis. This opens the outlet analysis form. You will notice outlet barrel sizing worksheet to the left and emergency spillway design to the right. The 10-year and the 100-year peak discharges are already populated in the form. I enter the outflow barrel details, its length, diameter, invert in, invert out and the barrel material type. I also enter the top of riser elevation. When I click on Compute, the program calculates the hydraulic head at the riser. The remarks field indicates if the water surface elevation in the riser is inside the riser or above the riser top, indicating inlet control or outlet control. The barrel's size, slope or material can be adjusted to ensure that the water surface elevation is inside the riser. Now I enter the emergency spillway details, its length, width and the emergency spillway top elevation. I also enter the top of embankment and the required freeboard. When I click on Compute, the program calculates the head above the weir. The remarks field indicates if the freeboard is adequate or not. I go to the top menu bar and click on File, Save. This will save all the data including results of outlet analysis. I go to the top menu bar and click on File, Print. The print report, which is in Excel format, gives the results of outlet analysis. A water balance calculation must be performed to assure that the constructed wetland can be supported by runoff from the contributing drainage area, and to assure the deep pools will not go completely dry during a 30-day summer drought. Equation 14.1 of the DCR specifications gives a simplified water balance equation for acceptable water depth in a wet pond. The program uses the more rigorous analysis, as given in Appendix 5C of Volume 2 of the DCR Stormwater Management Handbook. The maximum drawdown due to evaporation and infiltration is checked against the anticipated inflows during that same period. The anticipated drawdown during an extended period of no appreciable rainfall, which can be selected from the pull-down list, is checked as well. This will help establish a planting zone for vegetation, which can tolerate the dry conditions of a periodic drawdown of the permanent pool. This will also indicate the need or otherwise of a clay liner, if the native soils indicate excessive infiltration. I go to the top menu bar and click on File, Water Balance. This opens the water balance screen. You will notice that all accepting the infiltration rate of basin bed material, and the assumed number of days with no rainfall are populated. Default values are provided in these fields as well. The monthly precipitation and evaporation shown are from Appendix 5C of the DCR Stormwater Management Handbook. The user can always override the default values. I click on Compute in Section A of this worksheet. The remarks will let me know if there is positive water balance with or without liner. I now click on Compute in Section B of this worksheet. The remarks will let me know the maximum drawdown percentage in a 30-day drought situation. I go to the top menu bar and click on File, Save. This will save all the data including results of water balance analysis. I go to the top menu bar and click on File, Print. The print report, which is in Excel format, gives the results of water balance analysis. This concludes the design of wet ponds using SWMSOFTVA.